Classification is a technique that we can use to predict which class or category something belongs to. The simplest variant of this is binary classification, where we predict whether an entity belongs to one of two classes. It's often used to determine if something is true or false about the entity. For example, suppose we take a number of patients in our health clinic, and we gather some personal details and run some tests. And we can identify which patients are diabetic and which are not. We can learn a function that can be applied to these patient features and give the result 1 for patients that are diabetic and 0 for patients that aren't. More generally, a binary classifier is a function that can be applied to features x to produce a y value of 1 or 0. Now, the function won't actually calculate an absolute value of 1 or 0. It will calculate a value between 1 and 0. And we'll use a threshold value to decide whether the result should be counted as a 1 or a 0. When you use the model to predict values, the resulting value is classed as a 1 or 0 depending on which side of the threshold line it falls. Because classification is a supervised learning technique, we withhold some of the test data to validate the model using known labels. Cases where the model predicts a 1 for a test observation that actually has a label value of 1, are considered true positives. And similarly, cases where the model predicts 0 and the actual label is 0 are true negatives. If the model predicts 1, but the actual label is 0, well, that's a false positive. And if the model predicts 0, but the actual value is 1, well, that's a false negative. Now, the choice of threshold determines how predictions are assigned to classes. In some cases, a predicted value might be very close to the threshold, but it's still misclassified. You can move the threshold to control how the predicted values are classified. In the case of the diabetes model, it might be better to have more false positives, but reduce the number of false negatives, so that more people who are at risk of diabetes get identified. Now, the number of true positives, true negatives, and false negatives produced by your model is crucial in evaluating its effectiveness. The counts of these are often shown in what's called a confusion matrix, and this provides the basis for calculating performance metrics for the classifier. The simplest metric is accuracy, which is just the number of correctly classified cases divided by the total number of cases. In this case, there are 5 true positives and 4 true negatives, and there are also 2 false positives and no false negatives. That gives us 9 correct predictions out of a total of 11, which is an accuracy of 0.82 or 82%. Now, that might seem like a really good result, but perhaps surprisingly, accuracy actually isn't all that useful as a measure of a model's performance. Suppose that only 3% of the population is diabetic. I could create a model that simply always predicts 0 and it would be 97% accurate. But it's completely useless for identifying potential diabetics. A more useful metric might be the fraction of cases classified as positive that are actually positive. This metric is known as precision. In other words, out of all the cases classified as positives, which ones are true and not false alarms? In this case, there are 5 true positives and 2 false positives. So our precision is 5 out of 7, which is 0.71, or 71% of our cases identified as positive really are diabetic, and 29% are false alarms. In some situations, we might want a metric that's sensitive to the fraction of positive cases we correctly identify, and we call this recall. It's calculated as the number of true positives divided by the combined true positives and false negatives. In other words, what fraction of positive cases are correctly identified. In this case, there are 5 true positives and no false negatives. So our recall is 5 out of 5, which is, of course, 1, or 100%. So in this case, we're correctly identifying all patients with diabetes. Now, recall actually has another name. Sometimes it's known as the true positive rate. And there's an equivalent rate for false positives compared to the actual number of negatives. In this case, we have 2 false positives and 4 true negatives. So our false positive rate is 2 out of 6, which is 0.33. Now you may remember that the metrics we got were based on a threshold of around 0.3. And we can plot the true positive rate against the false positive rate for that threshold like this. If we were to move the threshold back to 0.5, our true positive rate becomes 4 out of 5, or 0.8, and our false positive rate is now 6, or 0.16, which we can plot here. Moving the threshold further to say 0.7 gives us a true positive rate of 2 out of 5, or 0.4, and a false positive rate of 0 out of 6, or 0. And if we plotted this for every possible threshold rate, we would end up with a curved line that looks like this. Now this is known as a receiver operating characteristic, or ROC chart. Now the area under the curve, or AUC as we call it, is an indication of how well the model predicts. Generally, you want to see a large AUC with the curve staying as close as possible to the top left corner of the chart. A perfect classifier would go straight up the left and then along the top, giving an AUC of 1. Now you can always compare with a diagonal line, and that represents how well the model would perform if you simply made a 50-50 guess. It's an AUC of 0.5, so you're just simply random guessing 50% of the time true, 50% false. In this case, our model has an AUC of around 0.9, so it's definitely outperforming guessing.